Hello everyone, welcome to the course Information Theory and Coding. In the earlier classes, we were discussing about average information content of a symbols in a long independent sequence, and we have found that the entropy of the each state will be calculated based on the emission of symbols which will be emitted at a particular state I will be calculated by using this expression. Similarly, the entropy of all the source will be calculated as summation pi into hi, where pi is nothing but the probability of the source which is being in that state, and we can able to calculate the average information rate which will be given as Rs, capital Rs is equal to small rs into h of s. And we have one theorem, that is that the entropy of the source will keep on reduces as the number of source symbols. Dependency will depends upon the with increasing the number of symbols. So let us try to solve one problem which is associated to the Morkov source in this class. So they have given you the given Markov source as shown in the figure. First you need to find out the entropy of the each set. Second one, the entropy of the source you need to find out. And finally, you need to find out G1, G2, G3, and you need to verify that G1 is greater than G2, G2 is greater than G3, and G3 must be greater than H. So for that, they have given you the tree diagram, and in the tree diagram, and they said that the initial probabilities of being in the state, either it may be in P1, either it may be in P2 or in P3. They have given the initial state probability will be given as 1 by 3, 1 by 3, and 1 by 3. Now let us try to find out the entropy of the each state. So when you want to find out the entropy of the each state, so let us consider a particular state 1. So here what are the symbols which has been emitted with the probability you need to calculate. So here the state S1, it is emitting a probability one symbol with a probability 1 by 2, and it is emitting one more symbol with a probability 1 by 4, and it is emitting one more symbol with a probability 1 by 4. So these are the three symbols which has been emitted by the source S1. So therefore we can calculate the entropy of the first state. It is nothing but summation j is equal to 1 to n pij log 1 by pij. It is nothing but, so P11 means being in the state 1, and it will go to state 1 OC, that is P11, and it emits a particular symbol and it will move to state 2, that is we call it as a P12, and here also in the state 1 it emits a one particular symbol and it will move to state 3 with a probability P13. So if I substitute that 1 by 2 log 2 plus 1 by 4 log 4 and plus 1 by 4 log 4 means we will be getting the entropy of the first state, it is 1.5 bits per symbol. Similarly, I need to calculate the entropy of the second state. So you can see here the probability of being in the state 2, it emits a symbol, particular symbol 1 by 2, and it will be remains in the state 2 only with a probability 1 by 2. And along with that, it is emitting two more symbols, that is with a probability 1 by 4, and it will go to the state S3, P3, and it is emitting one more symbol and it will move to the state P1 with a probability 1 by 4. So therefore, if I calculate the entropy of the second state, that is P21 log 1 by P21 plus P22 log 1 by P22 plus P23 log 1 by P23. So if I substitute these probability values, so you'll be getting 1 by 4 log 4 plus 1 by 2 log 2 plus 1 by 4 log 4. So ultimately you'll be getting the entropy of the second source, that is entropy of the second state, we will be calculated as 1.5 bits per symbol. Similarly, we need to calculate the entropy of the third state, that is P1 log 1 by 31, P32 log 1 by 32 plus P33 log 1 by P33. If we substitute all these expression, so you'll be getting the entropy of the third state is nothing but 1.5 bits per symbol. So now let us try to find out what is the entropy of the source. So in the last class, we have come up with the expression that the entropy of the entire source is nothing but it is a sum of product of being in the state, probability of the being in that state multiplied by the entropy of that state. So if you do that, P1 into H1 plus P2 into H2 plus P3 into H3, since all the probabilities are occurring with being present in that state will be 1 by 3 only in the given problem. So therefore 1 by 3 into 1.5 into 3. So you'll be getting the entropy of the Markov source, which is nothing but 1.5 bits per symbol. So now let us try to find out what is the second thing they have asked. So they have asked you what is the entropy of the symbols if you having only one symbol, that is called as a G1. What is the entropy of the symbol, that is a message, if you have a two symbols in that, and what is the entropy of the message if you have a three symbols in that. So you need to find out the number of symbols what is emitted if it is having only one symbol. You need to find out the messages which are having two symbols. You need to find out the messages which is having three symbols, and you need to show that the entropy of the G1 should be greater than to G2. This G2 should be greater than G3, and ultimately it has to be greater than the entropy of the source. So in order to do that, so first we need to write down the tree diagram for all the states. So how we have drawn this diagram is, let us consider over here. So you are in state 1 and you are going to emit a particular symbol, and you will be remain in a state 1 only with a probability 1 by 2. Similarly, when you are in state 1, you are going to emit a particular symbol and you are going to move to S2, that is 2, second state, with a probability 1 by 4. Similarly, when you are in state 1 and you are emitting a particular symbol and you are moving to S3, that is a state 3. So we need to consider the emission of the symbols in order to find out, so what are the symbols which has been emitted from this particular source. So therefore you can see here, when you are in state 1, you are going to move in state 1 only with the emission of probability of symbol 1 by 2. That is, therefore the probability of emitting a particular symbol and it is being in state 1 only, it is nothing but the transmission probability multiplied with the initial state probability. If you do that, you'll be getting 1 by 3 into 1 by 2, so you'll be getting 1 by 6. So means what? The probability of emission of a particular symbol when you are in state 1, which is nothing but 1 by 6. Similarly, when you are in state 1, you are emitting a particular symbol and you are going to move to state 2. So what is the probability of getting a symbol when you are in state 1 to state 2? It is nothing but 1 by 3 into 1 by 4, so you'll be getting a 1 by 12. Similarly, for the 3, so when you are in state 1 and you are going to emit a particular symbol with a probability 1 by 4, so that the probability of emission and you are being in this state 3 from state 1 to state 3, it is nothing but 1 by 12. So these are the way we call it as a probability values of a message having only one symbol. So from state 1, you got 1 by 6, 1 by 12 and 1 by 1. So similarly, you need to find out in the state 2. So when we see the state diagram for the 2, so when you are in state 2, you are going to emit a particular symbol and you are going to move to the state 1 with a probability 1 by 4. So therefore, initial state probability multiplied with the transition probability. If you do that, so you'll be getting 1 by 12. So when you are in state 2, you are emitting a particular symbol with a probability 1 by 2 and you are going to move to the state 2. So therefore, the probability of being in state 2 when you are in earlier case, you are state 2 only, that is 1 by 3 into 1 by 2, so you'll be getting 1 by 6. Similarly, when you are in state 2, you are emitting a particular symbol and you are going to move to state 3 with a probability 3 by 4. So therefore, the probability of getting a symbol from state 2 to state 3, it is nothing but 1 by 3 into 1 by 4, so you'll be getting a 1 by 4. So in state 2, we have a 3 symbols will be emitted with a probability 1 by 2, 1 by 6, 1 by 12. Similarly, if you calculate for the state 3, so when you are in state 3, you are going to emit a particular symbol and you are going to move to state 1 with a probability 1 by 4. So therefore, the probability values of being in the first state, so it is nothing but 1 by 3 into 1 by 4, you will be getting a 1 by 12. Similarly, when you are in state 3, you are going to emit a particular symbol and you are going to move to state 2, so you will be getting 1 by 4. So therefore, the initial probability multiplied with the state transition probability, if you do that, so you will be getting 1 by 12. Similarly, when you are in state 3, you are going to emit a particular symbol and you are going to be in this state only. So therefore, the probability of being in state 3 to state 3 after emission a particular symbol, it is 1 by 3 into 1 by 2, so you'll be getting a 1 by 2. So these are, we call it as a states at the end of the first symbol interval. So means what? If a symbols are emitted from the source, if it is having only one symbol means, then these are the state entropies or the probability of emission of the symbols what we are going to use it. So the same thing you are going to extend it for the second symbols. So you are in state 1, again if you emit a particular symbol and you are going to move to state 1 means, then you are going to have a probability of getting a second symbol will be the initial symbol what is 1 by 6 and multiplied by the state transition probability 1 by 2. So you'll be getting 1 by 6 into 1 by 12. So this is the probability of getting a 2 symbols from the Markov source when you are in state 1 to state 1. So next one. So when you are in state 1 and if you emit a particular symbol, again you are going to move to state 2. So therefore, the probability of getting a symbol from 2 sources, that is if a message is having 2 symbols means, so it is nothing but 1 by 6 into 1 by 4. So like this, you are going to calculate for all the emission from the particular state, that is from the state 1 and similarly from the state 2 and similarly from the state 3 you are going to getting. So these are the states at the end of the second interval. Now let us try to find out what is this Gn. So we know that in the earlier classes we calculated Gn is nothing but 1 by n summation Pm into log of 1 by Pm. So where Pm is nothing but the probability of emission of the particular symbol, and N is nothing but the number of messages symbols in a particular message. So if you consider the first state at the end of the first symbol transmission, then N will be having only one symbol in a message. So therefore I can calculate G1 is nothing but 1 by 1 summation 1 to 3, because 3 symbols are emitted at a particular from each state. So therefore you can calculate is Pm Pmi log 1 by Pmi. So see what is this Pm? It is nothing but when you see that, so you'll be getting 1 by 3 log of 3 you'll be getting. So therefore we can calculate G1 is 1.585 bits per symbol. Similarly, where for the N2, so the message is having two symbols. So means we need to consider these probability values. So if I consider these probability values, so you will be having totally 9 symbols with different probability values what you are going to consider. So if I calculate this G2 1 by 2 summation I is equal to 1 to 9 Pmi into log 1 by Pmi, then you are going to get G2 is equal to 1.5425 bits per symbol. Similarly, if I extend for the third case, means if the message is having 3 symbols, means then totally you will be getting 27 different symbols, and if I calculate the G3 by substituting all these expression, means then you will be getting G3 is equal to 1.528 bits per symbol. So therefore you can see here G1 is 1.58, G2 is 1.54, means it has been reduced, and G3 is 1.28, again it has been reduced, and you can see what is H of S. H of S is 1.5. Therefore its holds good property, that is G1 is greater than G2 is greater than G3 when it is compared to the entropy of the source. Okay, so the remaining we will see it in the next class. Thank you.